All right, I wrote a few questions from my textbook, and hopefully they help you with some of this hydrogen line spectra stuff. In the line spectra of neon, the most prominent line is wavelength 865.438 nanometers. There are other lines at these wavelengths. In what region of the electromagnetic spectra are these found? This is basically going to be helpful if you just remember two numbers. If you remember that visible light is between 400 nanometers and 700 nanometers. The long wavelength side is red. That's the 700 nanometers. And the 400 nanometers is blue or violet. That means anything longer out here or shorter out here are invisible to us. And the kind of light with longer wavelength that we can't see is infrared. And the shorter wavelength that we can't see is ultraviolet. So if you look at these numbers, 865 nanometers is on the infrared side of visible light. So if you remember, visible is 400 for blue and 700 for red, you'll know that bigger numbers are infrared and smaller numbers are ultraviolet. Now, there are microwaves and radio waves. They're way, way far away. They don't even use nanometers for those. Which of these lines has the most energetic radiation? Well, the way to remember this is this equation. The speed of light is the wavelength times the frequency. The energy of a photon is equal to a constant times the frequency, or it's two constants over the wavelength. So that means that the highest energy has the shortest wavelength. Okay? And so for that one, the 837.761 nanometers is the one with the shortest wavelength. Finally, what is the frequency of the most prominent line? The most prominent line is 865.438 nanometers. And then we're going to figure out what the energy is. So, the first thing I want to do is change these units. So 865.438 nanometers, I already want to remember that 1 nanometer is the same as 1 times 10 to the minus 9th meters. Always remember that the prefix is substituted by the power. And that gives me 8.65438, it's a lot of sig figs, times 10 to the minus 7th meters. Now I could use the equation that I mentioned above. Planck's constant is 6.626 times 10 to the minus 34th joules times seconds. The speed of light is 3.00 times 10 to the 8th meters per second. And I just wrote down the wavelength. And I end up getting 2.297 times 10 to the minus 19th joules. That's the energy. Whoops, I didn't do the frequency. Sorry. In order to do the frequency, I would use this equation, and I would take the speed of light divided by the wavelength as the frequency. So I didn't do that here, but you could do that. I should have said this earlier. Maybe you should try these problems on your own, and then you could play mine and see what the answer is. Consider transitions involving the n equals 1 to n equals 4 energy levels. How many emission lines are possible? Oh, this one's pretty easy if you just draw a little picture. So remember how we talked about yesterday that the spacing keeps getting smaller? Oops, n equals 4. So I got 4 lines here. I'll use yellow to draw the lines. So all the possible lines are 2 to 1, 3 to 1, and 4 to 1, 4 to 2, and 3 to 2, and then 4 to 3. So there's 6 possible lines. Remember how this works. emission is when the atom is in an excited state and it falls to the ground state. Now, all of these questions are about H atoms, which are super easy because there's only one electron. So these are all the different possibilities of transitions that are emissions. So that's energy going from a high level to a low level. If it was the other way around, you'd call it absorption. So arrow up is absorption. All right, photons of which transition have the lowest energy? The lowest energy is going to have the longest wavelength. That's going to have the smallest frequency. Those really don't answer the question, I realize now. The lowest energy, you just simply look at the picture, and the tiniest arrow is the n equals 4 to the n equals 3. That's easy to see, again, because these spacings are constantly getting smaller, and that's going to be the smallest arrow. The emission line with the shortest wavelength, short wavelengths, means high frequency, high energy. The longest energy one is going to be the n equals 4 to the n equals 1. All right, so if the energy absorbed by a hydrogen atom in the ground state, the atom is excited to a higher energy state. Let's draw the picture that I did on the previous one. Try to draw it neater with a little bit more space. So n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So the point again, Margaret, is that each of these levels is up higher than the previous level, but the spacing always gets smaller. So if I am interested in comparing things to this transition, n equals 3, which of the following transitions requires a longer wavelength? A longer wavelength than this. And now let me just draw in the pictures and see what we get here. So I'll pick another color. Please don't think that that's the color of this light, but I'm just drawing it because I make it easy to see. 2 goes to 4, 1 goes to 5, 1 goes to 4, and 3 goes to 5. Okay? So reading the question again, which of the following transitions requires a longer wavelength? Longer wavelength. Okay, so if you remember these equations, or if they give them to you on the test, you should use them. What does it mean when I have a long wavelength or a large wavelength? If I have a large wavelength, I have a small frequency. Smaller frequency. And if I have a smaller frequency, ta-da, I have a smaller energy. You probably could have figured that out by looking at this equation just with wavelength, but that's the way I decided to do it. All right, so which of these green arrows has a smaller energy comparing to n equals 1 to n equals 3? Well, that's obvious. That's this arrow here and that arrow there. So n equals 2 to 4 and n equals 3 to 5 are both longer wavelength. All right, one more. Calculate the wavelength and the frequency when an electron changes from n equals 4 to n equals 3 in the H atom. In what region of the spectrum is the radiation found? Now, my book has 2 different equations for this. I'll do the energy one first, and that will give me frequency. So let's see, what color will I use? I'll use blue. So I have an equation in my book. Again, I don't know what your book says, but it says the difference in energy between 2 levels is equal to a bunch of constants times 1 over the final level squared minus 1 over the initial level squared. Okay, and so this is for an emission. Okay, so this is a downward arrow from the n equals 4 to the n equals 3. That's what we're looking at. So my book has that those three constants together is this value, minus 1,312 kilojoules per mole, and then the final level is 3 squared, and then the initial level was 4 squared, and so I end up getting an answer of minus 63.78 kilojoules per mole. But that's per mole. So what if I want to know the joules per photon, and then I could go to the wavelength and the frequency. So 1 mole is the same as 6.022 times 10 to the 23rd photons, and 1,000 joules is the same as 1 kilojoule, and that gives me 1.059 times 10 to the minus 19th joules per photon. Okay, so I could go a couple of different ways here. E equals hc over lambda. If I plug everything in, I end up getting 1.876 times 10 to the minus 6th meters, or 1876 nanometers. You might remember from my earlier discussion that's longer than visible light. That's going to be infrared. The frequency is going to be the speed of light over the wavelength. And let me do that quick. Hope I do this correctly, because I didn't prepare for this. Divided by, I'm going to do the wavelength. I just saw a mistake. Get 1.6 times 10 to the 14th inverse seconds. I messed up this equation before. I got these backwards. That was the wavelength is equal to that. So I just flipped those around, of course. Okay, so that just swapped. All right, so I hope this helps. If you think of anything else, just send me a note. Bye.